All right, this is section 5.7 on complex zeros and the Fundamental Theorem of Algebra. Our objectives for this section are to use the conjugate pairs theorem to find a polynomial function with specified zeros and to find the complex zeros of a polynomial function. Let's start off with using the conjugate pairs theorem here. Well, we're going to start off with a definition of complex zeros. A variable in the complex number system is referred to as a complex variable. A complex polynomial function f of degree n is a function of the form f of x is equal to a sub n times x raised to the n power plus a sub n minus 1 times x raised to the n minus 1 power plus so on plus a sub 1 x plus a sub 0. Where a sub n sub 1, and so on up to a sub 1, a sub 0 are complex numbers, and a sub n is not equal to 0, and n is a non-negative integer, and x is a complex variable. And as before, a sub n is called the leading coefficient of f, and a complex number r is called a complex zero of f, if f of r is equal to 0. Okay, so you might have noticed over here on the side, I started drawing a Venn diagram. Because now that we're using this word complex, I know some people are going to be wondering, well, what does that mean? Let's recall the real number system. The real number system is made up of two sets of numbers. The irrationals, which are non-terminating and non-repeating decimals, such as pi and such as the square root of 2, and the rationals, which are made of other subsets of numbers, such as the integers, the whole numbers, and also the natural numbers. The natural numbers are also called the counting numbers because those are the numbers you learn to count by, like, for example, 1, 2, and 3, and so on. Okay? Now, say I were to decide to add on to this number system of the real numbers, and I decided to add some more to it, right? We could actually create a number system where the real numbers is a subset of that number system, and we can call that the complex number system. So the complex number system is made up of, basically, similar to the real numbers, two sets of numbers. It's made up of the real numbers, and it's made up of complex numbers that are not real. So the complex numbers that are not real, we can write those of the form a plus bi. And the subset of this number, or this set of numbers, would be the pure imaginary numbers. So pure imaginary numbers would be numbers that just have that imaginary part. So they could be like numbers like I, or maybe like a number like 3i, something like that. You could also have like a negative 3i. By now, hopefully everybody knows what I is. It's the imaginary unit, right? The square root of negative 1. So hopefully everyone remembers that what I represents. All right, that's our complex number system. So when I'm talking about complex numbers and these complex zeros, just recall that, the real numbers fall into this number system. So when we're talking about, complex polynomial function, we're still working with the real numbers. But now we can also talk about numbers that are not real. Okay? So that's all it means. I don't want anyone to freak out there. The Fundamental Theorem of Algebra says that every complex polynomial function f of a degree n greater than or equal to 1 has at least one complex zero. And the theorem The following theorem says every complex polynomial function f of degree n greater than or equal to 1 can be factored into n linear factors not necessarily distinct of the form f of x is equal to a sub n times the quantity x minus r sub 1 times the quantity x minus r sub 2 and so on times the quantity x minus r sub n, where a sub n, r sub 1, r sub 2, so on up to r sub n are complex numbers. That is, every complex polynomial function of degree n greater than or equal to 1 has exactly n complex zeros, some of which may repeat. So now the degree of the polynomial function, that's going to tell you how many zeros, right? And if it's got that many zeros, n number of zeros, it's got n number of factors as well, right? The conjugate pairs theorem. Suppose f is a polynomial function whose coefficients are real numbers. If r is equal to a plus bi is a zero of f, the complex conjugate is going to be a minus bi, which is also a zero of f. So for example, let's say I said 3 plus I is a zero of f. What would be the complex conjugate of 3 plus I? The complex conjugate of 3 plus I is 3 minus I. Right? So we call these two numbers complex conjugates of one another. So these complex conjugates, it's like, you know, when you're looking for zeros, if you find out that one of these is a zero of a polynomial function, then its complex conjugate has to also be a zero. They come in pairs, so that's the way they work, okay? So 3 plus I is a zero of f, so that means that 3 minus I is also a zero of f. So this is an important theorem. We're going to be using this theorem quite a bit in this section, right, in order to find our zeros and to find our factors of our polynomial functions. Corollary: a polynomial function f of odd degree with real coefficients has at least one real zero. Well, if you have a polynomial function of odd degree, we've already talked a little bit about, you know, what are certain end behaviors of polynomial functions with odd degree. So if we have something that says something like y is equal to x raised to an odd power, we already know that the function is going to look something like this, where it starts off down from negative infinity and it rises up towards positive infinity for the y values, right? But we just don't know what's happening inside. And if we have y equal to negative x raised to an odd power, then it's going in the opposite direction. It starts up from the top and it works its way down. So of course it's got to have at least one real zero, because of course it's going to have to cross the x-axis at least once, right? All right. Number 1, we're ready to start off our first problem. Find the remaining zeros of f of x whose coefficients are real numbers, given that the degree of f of x is 4 and the zeros are 2 minus I and negative I. Let's start off with 2 minus I. If you already know that you have a 4th degree polynomial and 2 minus I is a 0, we just talked about, right, that complex conjugate theorem. We're going to need to have the complex conjugate of 2 minus I. So that's going to be 2 plus I. Remember, we said these come in pairs. And as for negative I, the complex conjugate of negative I is just going to be positive I. So this is 1, 2, 3, 4. There's your 4 zeros. Because this is a 4th degree, we know it has to have 4 zeros, 4 complex zeros. So the remaining zeros of f of x are going to be 2 plus I and positive I. And that's it. We're done for that problem. Okay, let's go ahead and go on to the next one, our next theorem here. It says, find a polynomial function with specified zeros. Theorem: every polynomial function with real coefficients can be uniquely factored over the real numbers into a product of linear factors and or irreducible quadratic factors. Number 2 says, form a polynomial f of x with real coefficients having degrees 5 and zeros, 1 with multiplicity 3, and 1 plus I. Answers may vary depending on choice of the leading coefficient. So if the degree is equal to 5, where there's got to be 5 zeros, right? And the zeros that we know of so far are 1 with multiplicity 3. That means that's like 3 zeros right there, 3 zeros of 1, and 1 plus I. So we need to think here, if we're trying to form this polynomial with real coefficients, I need to write out all the zeros that I have, and then I can write out the factors. If I know I have a 0, and let's say that 0 is equal to c, then that means I have to have a factor that's equal to x minus c, right? We talked about this. We talked about this in the factor theorem that we covered in our last section. We have a 0 of 1, which means we have to have a factor of x minus 1. Now, because they told us that the multiplicity was 3, we need to have 3 of these factors. So the power on this x minus 1, it's going to have to be x minus 1 quantity cubed, right? It's got to have a power of 3, because that's what's going to show that it's going to be multiplicity 3. Now, this is degree 5. If I've already got 3 factors here, or that represent 3 of my zeros, like imagine I took that 5 and I went like 5 minus 3 and I ended up with like 2. That means I'm missing 2 more factors, 2 more zeros. So this is how I want you to think. You're constantly thinking in terms of what's the degree of the polynomial, and you're kind of thinking away in terms of subtracting, okay, how many factors have I found? How many zeros have I found? How many more am I missing? So I know I've got 1 plus I, which means the factor for this one is going to be x minus 1 plus I. If I've got 1 plus I, then I also have to have 1 minus I, the complex conjugate of it. So the factor associated with that one is going to be x minus 1 plus I. So this is like my 2 other factors that I was missing right here. Right? Now, what do? I have found all the factors of this polynomial, but it wants the polynomial with real coefficients. What does that mean I have to do? That means I'm going to have to take all of these factors and I'm going to have to multiply them and simplify it all out. That's what it means, okay? It's a little bit of work, but we can do it. First off, we need to choose a leading coefficient here, right? I think the easiest leading coefficient to choose is always going to be the number 1, right? So my choice, if they're going to give me my choice for choosing any leading coefficient that I want to choose, of course, I'm always going to choose a leading coefficient of 1, right? Where your a equals 1. So that's just my suggestion to you. You know, if you want to make life easier on yourself, just choose a equal to 1, right? So much easier. So there's my 1 right in the front, right? You can't see it, but it's there, trust me. And then we have x minus 1 quantity cubed times, I messed up here a little bit, let me fix that, times x minus 1 plus I, and then I have x minus the quantity 1 minus I. There it is, right? And once again, my a is equal to 1. I already mentioned this, it's right there. I know you can't see it, but maybe I should state it right here just to make sure everyone realizes that I chose my own leading coefficient, and I chose the leading coefficient of 1 because it's the easiest one to choose. Okay, I think we're ready to do this, you guys. What do you guys think? Yes? Yeah, let's just go with a yes. I'll pretend everyone said yes. All right. So what did we say we have to do? We said we have to basically multiply all of these factors out. So let's go ahead and write this out again, and let's just kind of take it step by step, you know, little by little. x minus 1 times x minus 1 times x minus 1 times x minus the quantity 1 plus I times x minus the quantity 1 minus I. All right, let's start off with multiplying the x minus 1s. All right, so we do ultimately want to multiply all three of those x minus 1s out, right? So we want to multiply x minus 1 times x minus 1 times x minus 1. But you know what? If I multiply all three of these out, you know, that's going to be a little overwhelming to do it all at once. So why don't we just focus on multiplying two of those factors at once? I think that's easier for everybody, right? Everyone agree? Yes. Let's multiply x minus 1 times x minus 1. If I multiply this, that's going to give me a perfect square trinomial. And you guys all know how to come up with that perfect square trinomial because we've talked about this before, right? So I'm just going to go ahead and write it out. X squared, and that should be a minus 2x plus 1, right? If you need to FOIL it out yourselves, if you need to use the box method, then go ahead. Here I'm going to distribute this minus sign because I'm going to have to simplify this out a little bit more. So we're going to simplify it by distributing. Good, excellent. Now, what should we do next? We're going to have to multiply that trinomial with that binomial, right? That x squared minus 2x plus 1 times that x minus 1. I'm going to use the box method, okay? I know you guys, some of you guys don't like the box method, but I think you're really going to appreciate it in this example. You're going to see why I've learned to love it so much. So if you guys don't want to multiply using the box method, you can multiply using any other method you know of, and that's fine. But this box method keeps me nice, neat, and organized, and it just makes it easier for me to find my like terms that I can combine. All right. Now that I use the box method to come up with all the terms that I need there for the product, I'm going to move this over here to the side, and I'm just going to write this down. So here we're going to get f of x is equal to x cubed minus 3x squared plus 3x minus 1. Excellent. Now when I multiply these next two, I'm going to combine kind of like the x minus 1 together, like kind of like think of it almost as a term as I'm multiplying this, because I want you to notice here that we have x minus 1 here, we have x minus 1 here. We have I here, we have I here. And then look in the middle. We have a minus and a plus. These are like complex conjugates, right? Do you guys remember? Right? When you have the opposite sign here in the middle, but everything else looks the same, how to multiply that out? You can use that little trick, you know, to help you do a little faster, but let's just pretend you don't see it. Let's pretend we didn't, you know, you didn't see it that way. I'm going to use the box method to multiply this out. And then maybe that way you can see the pattern here so that you don't have to use the box method for when you're multiplying complex conjugates together, and you could work this out a little bit faster. So notice here we're going to come up with a negative x minus 1i, and then here's a positive like x minus 1i. And over here we have the negative I squared, which is just negative times negative 1, which is a positive 1. So look at what happens here. You see these two expressions? They're going to cancel out, right? That's always going to happen when you multiply by complex conjugates. So all I have to do is just basically combine this x squared minus 2x plus 1 with this plus 1. And when you add 1 plus 1, that's just going to turn that constant part into a 2. I'm going to show the steps up here as I'm writing this out, you know, just so that people can see the steps written out as well and not just see it in the box there. Okay, so it looks like I finally got this thing simplified out where I'm finally able to combine my like terms here. Now we're going to have to multiply this out. I know what you're thinking, right? A polynomial with 4 terms and a polynomial with 3 terms, right? This is when you learn to really appreciate and learn to love the box method. So I know there's still some people who are like, why do you use the box method? You know, this is why I use the box method, so that when I teach college algebra and I have to multiply these type of polynomials together, I don't make a mistake. It keeps me nice, neat, and organized. And I strongly encourage those of you that are struggling with these type of problems to adopt the box method. And you will see that it will make your life a whole lot easier. Okay, so we're just going to go ahead and multiply this out. I'm just going to write down each one of these terms here. And so this is what I got. Now I'm going to look for like terms. Like terms are all of the terms that, you know, have the same variable raised to the same power, and I can combine those together. All right, so now let's write down what's going to be our final function. Right, this is what we were looking for, right? We were looking for this function. So our final function is going to end up being, just trying to get that to fit right there. Perfect. All right, our final function is going to be f of x is equal to x to the 5th, and add your like terms. This is going to give me negative 5x to the 4th, and then this will be positive 11x cubed minus 13x squared plus 8x minus 2. Box in your final function, and there you go. Number 3, use the given 0 to find the remaining zeros of the function. The function here we have is h of x is equal to 3x to the 4th plus 5x cubed plus 25x squared plus 45x minus 18. 0 that we're given is 3i, and that's all we're given. This is a polynomial that has 5 terms. So if I want to factor this out, you know, I'm not going to be able to because I don't really know any techniques. I'm going to have to use this 0 that was given to me. We know that if you have a 0c, then the factor that's associated there with that polynomial function is going to be x minus c. I have a 0 of 3i, which means I need to have a factor of x minus 3i, right? And if I have a 3i, I also have to have a 0 of negative 3i because that's the complex conjugate of 3i. So I have to have a I have to have a factor of 3 minus negative 3i, which will simplify to x plus 3i. How are we doing? So far, so good? Yes, good. I like to hear that. Should we go on? Yes, okay, I'll take that as an enthusiastic yes. All right. The degree of this polynomial is a 4th degree. I have 2 of the factors here, 2 of the zeros. So I'm missing 2 more. It's always good to know, what am I looking for? Where am I at? Where am I headed? You know, so always go back and reassess, like, what have I found? What am I looking for? What was the original degree? You always go back and reassess, you know, where am I at? I'm going to go ahead and take the 2 factors that I do know of, and I'm going to multiply those together. When I multiply those 2 together, I end up with x squared minus 9i squared. But I squared by definition is just equal to -1, so I'm going to replace I squared with a -1, so it's -9 times a -1, which is x squared plus 9. That's the factor that I'm going to divide my polynomial by. Now, unfortunately, this factor is not of the form x minus c. If it's not of the form x minus c, I cannot use synthetic division, which is like my favorite form to use to dividing polynomials because it's so much easier than long division, right? So unfortunately, we are going to have to use long division on this particular problem, but hey, that's okay, right? Because we all love long division as well, and we all know how to do it. And it's just precisely for these type of situations that we need to know how to use it. All right, so let's go ahead and do some fun long division. We're going to divide x squared plus 9 into our polynomial function that we have right over here. I'm just going to copy it down from what h of x is equal to. And so we've got there 3x to the 4th plus 5x cubed plus 25x squared plus 45x minus 18. There we go. Now we're ready to divide. You're going to focus, making sure that both of these polynomials are written first in descending order. All right, so please make sure they're in descending order. It's going to make life a whole lot easier for you. We need to figure out what we need to multiply the x squared by to turn it into 3x to the 4th. I need to multiply by 3x to the 2nd. So 3x to the 2nd times x squared gives me 3x to the 4th. 3x to the 2nd times 9 gives me 27x squared. Now I subtract. My 3x to the 4ths cancel out, and I bring everything else down, and I repeat the process. That's the process of long division. In order to turn x squared into 5x cubed, I need to multiply by a 5x, a positive 5x. So if I multiply by the x squared by 5x, I get 5x cubed, and 5x times 9 gives me 45x, and now I subtract, because that's what you do when you divide. We subtract in this step, and now the 5x cubes cancel out, and the 45x is also happen to cancel out. Last but not least, we're going to multiply by a -2 to the x squared, so we can turn it into that -2x squared. So -2 times x squared is -2x squared, and -2 times 9 is -18. Now we subtract, and when you subtract negatives, you turn them into pluses, right? Positives, and these happen to cancel out. Now you better end up with a 0 as a remainder here, okay? Because if you don't end up with a 0 here, then you did not choose the correct divisor. This divisor, whichever one you end up dividing by, has got to divide evenly if it truly is a factor of our polynomial function. All right. Just trying to make more space here because this problem is kind of like, it's one of those problems that's it's got a lot of steps, so I'm just trying to make sure I got enough space for everything. And I like to show every one of my little steps here, right? All right, now I'm going to rewrite my function into the factors that I have found so far. So here I have h of x is going to be equal to, I'm going to write the x squared plus 9 first, the one that I just divided by, used as my divisor, and then times that 3x squared plus 5x minus 2. So now I already know the zeros of the x squared plus 9. I don't know the zeros of this thing here. Let's factor it, right? We know how to factor this, and this happens to be factorable. Not all of your quadratics here, or polynomials that of degree 2 that we get here are going to be factorable, but this one happens to be factorable, which means we lucked out. That makes this problem a little nicer for us, right? I'm going to use factoring by grouping since I do not have a leading coefficient of 1. You can also use trial and error, all right, if you don't want to do factoring by grouping. I'm going to factor out a 3. Make sure you have a plus sign in the middle, right? When you do factoring by grouping, your notation, it's all about the notation. I'm going to factor out a 3x out of the first binomial, and I'm going to factor out a negative 1 out of the second one. Now I can factor out an x plus 2, and I'm left with a 3x minus 1. Good. Now I can set each one of these factors equal to 0 because I now know that the factors of f of x, I've got that x squared plus 9 times the x plus 2. Oh, let me first write down the original trinomial I had there. And then let me write down the x squared plus 9 times the x plus 2 times the 3x minus 1 because we factored it out. Now I'm going to set each one of these new factors that I just found equal to 0 so that I can find the zeros of this polynomial function. I get x equal to negative 2, and I get x is going to be equal to 1/3. Therefore, I have found my zeros. The remaining zeros, right, the ones that weren't given to me, are going to be basically that negative 3i, that complex conjugate of the one that was given, negative 2, and 1/3. Let's go ahead and box that answer in, and we're done with this one. Good job, you guys. All right, number 4. Now we're ready to find the complex zeros of a polynomial function. So 4 says, find the complex zeros of the polynomial function and also write it in factored form. So this is a 2-part question. Part 1, find the complex zeros. Part 2, write the polynomial function in factored form. All right, let's start off with part 1. Trying to find those polynomial functions. Oh, sorry, trying to find those complex zeros. Looking at this polynomial function, my first thought is, hey, maybe I should try to factor this. It's got 4 terms. Maybe I can do factoring by grouping. But looking more closely at it, I realize, no, I cannot factor this by grouping, right? So this is not factorable. Because this polynomial is not factorable, I'm going to use my rational zeros theorem. Remember, that's where you find the factors of your a sub n and the factors of your a sub 0. P is going to represent the factors of the a sub 0, in this case the 85, and Q is going to represent the factors of the a sub n, the leading coefficient, and this is the 1 in this case. We're going to write this in the form of a ratio, P divided by Q. So Let me find the factors of 85 first. 85 is 5 times 17, so that means the factors of 85 are going to be 1 times 85 and 5 times 17. So those are all the factors I can get from 85. So if I'm going to write these ratios as P divided by Q, or P over Q, let me write step 1 first, right? Because I know some people sometimes like it when I write steps. Step 1 is going to be use rational zeros theorem. And the reason I'm using the rational zeros theorem is because f of x cannot be factored, but you're always trying to find the easiest way to do these problems. The first thing I would have tried is I would have tried factoring, but it just didn't work for us this time. So we use the rational zeros theorem. We're going to have to find out all the ratios of P over Q. So I'm going to write down all the factors here of 85. I got positive -1, positive -5, positive -17, and positive or negative 85. And the possible factors of Q, of A sub n, which represent our Q, are the positive or -1. That means all the simplified ratios would be positive or -1, positive or -5, positive or -17, positive or -85. This basically means that I'm going to have to try number 1, -1, positive 5, -5, 17, -17, 85, and -85. Let me just rewrite that 5 as just a 5, because I know someone's going to be thinking, why did you put a plus sign in front of that one and not the 17 and 85? And I don't want people thinking that. I'm trying to be consistent. So now that we know that these are all the possibilities for our rational zeros, right? If there are any rational zeros, they're in this list of possibilities. We're going to have to now use let's call this step 2. We're going to have to use the let's use the remainder theorem, and let's call it also the factor theorem, because I'm kind of using a combination of both of these here. The remainder theorem says that if I substitute a value in place of x, the value that I get it to equal to, the y value that comes out, is the remainder of if I would have divided by that factor of, like, in this case 1, if I'm using this 1, so if I would have divided by the factor like x minus 1, right? That's c, and then the x minus c factor, right? That's how it's associated. It's giving me the remainder. So my function f of x is equal to x cubed plus 13x squared plus 57x plus 85. I'm going to find f of 1. And whatever it tells me f of 1 is equal to, that's the remainder that I'm going to get from this. So f of 1 is equal to 156. That's a remainder of 156. My goal is to have a remainder of 0. This is not a 0. Therefore, what does that mean? I keep on going. I'm not going to use 1. I'm going to cross it out. My next one is -1. F of -1, plug it in. I would just go ahead and plug this into your calculator. I got f of -1 in the calculator is a 40. It's not a 0. You keep on going. Let's try f of 5. F of 5 is equal to 820. That is not a 0. We keep on going. Let's try -5. F of -5 is equal to, yes, it's a 0. Yay. This is when you do your happy dance. Go on, I'll give you a chance. Stand up, do your happy dance, and yell, yay. So we found our 0. It's -5. Now what? What does that mean, right? Well, let's write down first of all that this means that -5 is a 0. Now, what else does it mean? Well, this also means that x minus a negative 5 is a factor of the polynomial function. And we can, of course, simplify x minus negative 5 to x plus 5. So we can say x plus 5 is a factor of the polynomial function. Right? Pretty cool. So now that we found that x plus 5 is a factor, now what? X plus 5 is of the form x minus c, right? Because we can write it as x minus a negative 5. Therefore, my c is negative 5, right? Because it's of the form x minus c, what does that also mean? This means that x plus 5 is of that form x minus c, right? And I already mentioned this. I mentioned that we could write this as x minus a negative 5, so you can write it as a subtraction, right? Then that means that you can use synthetic division. That's what it means. Because remember, we said you can only use synthetic division if the factor is of the form x minus c. This is another yay. This is another opportunity for you to get up and do your happy dance. Go ahead, do it. Get up and do your happy dance. All right, now we're going to substitute here where our c goes. Instead of c, we're going to put our 0, which is that negative 5 to do our synthetic division. And then up here, we're going to put the coefficients of our polynomial function. So we've got a 1, a 13 there, a 57, and an 85. Okay, let's write in all of these coefficients, right? Make sure it's got to be in descending order. Make sure your polynomial is in descending order when you do this. And you have to account for every single term. And your 0 here, or your c value, is the negative 5. Let's bring down that 1 first. Multiply 1 times negative 5. It's negative 5. And 13 minus 5 is going to give me 8. 8 times negative 5 is negative 40. 57 minus 40 is 17. 17 times negative 5 is negative 85. And 85 minus 85 is a 0. Yay. Once again, this better be a 0. It has to be a 0 because that means the factor we chose divides evenly into our polynomial function, and it gives us a nice a nice polynomial as a result, as the quotient with no remainder. That's what your goal is. So our polynomial that's left over, our polynomial factor that's left over, is x squared plus 8x plus 17. So right now is a good time to write out what do we have so far in terms of our factored polynomial function. Let me write this. I forgot to write down my steps here. Let's say step 3 was the synthetic division step for my peeps out there that like to write out the steps. All right, that's for you guys. All right. Where was I? Oh yeah, let's write this function now, factored into the factors that we have so far. So far we have f of x is equal to, well, let me write down the original function first so we can make that connection. Those of you that are still trying to make this connection, this is the original function we started off with. These are the factors we have for this function so far. F of x is equal to the quantity x plus 5 times the quantity x squared plus 8x plus 17. Now, we need more factors, right? Because this is originally a third degree polynomial function. And I need to split this up so I can find each one of those zeros. I need 3 zeros. I need 3 factors. Let's set this factor equal to 0 and let's try to solve it. My first attempt at solving this would, of course, be to try to factor the trinomial using the magic x method. Unfortunately, there are no numbers that will multiply to give 17 and add up to give 8. Therefore, this is not factorable. Let's use completing the square. You can also use the quadratic formula, but I just think completing the square is easier in this case because we have a nice 8 in the middle there for our coefficient. Half of 8 is 4, and 4 squared is 16. So I'm going to add 16 to both sides. I have completed the square because I've turned this into a perfect square trinomial on the left. I'm going to factor it into x plus 4 quantity squared is equal to -1. Take the square root of both sides, and we get x plus 4 is equal to plus or minus I. I'm going to subtract 4 from both sides, and we get x is equal to -4 plus or minus I. These are the two remaining zeros I was looking for. So it's a third degree polynomial. It's got to have 3 zeros. We had x equal to the -5, right, for that first zero. And then these are the other 2 zeros that we were missing. -4 plus I and -4 minus I. Now, let's go ahead and write out the zeros that we found. And let's write out the corresponding factors to these zeros. So this is going to be x minus the quantity -4 plus I. And then the other zero we found here was -4 minus I. And the corresponding factor for that zero is going to be x minus the quantity -4 minus I. I've got all the factors I need here in order to write out the factored form of this polynomial function. So why don't we go ahead and do that? All right, so we have f of x is going to be equal to, remember that original factor that we had found earlier, that x plus 5, and then we're going, that was from up here from earlier. Remember we found that by using the rational zeros theorem. And then we had x minus that quantity -4 plus I, and x minus the quantity -4 minus I. Now here I can simplify this a little bit more by distributing this minus sign. So let's go ahead and do that. So this is now going to simplify to f of x is equal to x plus 5 times the quantity x plus 4 minus I times the quantity x plus 4 plus I. Now let's write down the zeros, right? So it was this was a remember this was a two-part question. It wanted the zeros and it wanted the factored form of the function. The zeros are going to be -5, -4 plus I, and -4 minus I. And let's box that in. And we are done. Good job, you guys.